Thank you. Thank you for inviting me to speak. And I'm very sorry that I could not be there. I had been really looking forward to this, but some unfortunate personal situation meant that I was unable to um, travel this week. So I am going to talk about universal distributions of groups and algebraic objects. So this is going to be a broad overview talk about some ideas that are connected to a lot of the universality results in number theory, but go in a different direction where the kinds of objects that we are seeing probability distributions of are a bit different. Okay, so just to begin, um, so I'm talking about universality in the sense that we're familiar with that probabilistic systems that are built from many usually independent random inputs have output or macroscopic behavior insensitive to the input distributions. And so I know there are a lot of familiar examples, maybe always starting with the central limit theorem, Brownian motion, eigenvalues of random matrices. I mean, of course, there are too many to list. But a lot of the distributions that arise as this macroscopic behavior are distributions that are distributions on the real numbers, or it could be the complex numbers, or some r to the n or c to the n, or some distribution on a space like that. In contrast, these days in arithmetic statistics, we're often asking about distributions of groups as opposed to just distributions of numbers. So, for example, some of the main headline kind of groups of interest might be things like class groups of number fields or Selmer groups of elliptic curves, or maybe fundamental groups of curves over finite fields. And so these are all distributions arising in algebraic number theory, arithmetic geometry, that we're trying to understand how often do we see which kind of groups. And it turns out that many distributions that arise from these questions, depending on the exact flavor of the question and the case, either that are arising empirically, what we're seeing in numerical data, or conjecturally, or sometimes provably, depending on the situation, are universal in this same, bird's eye view description of universality that I gave here. But the universal distributions, are quite different, and um, and introduce these new classes of important distributions that are distributions on groups or related algebraic objects that have their own, important universality properties. So um, maybe the first important example of this is the Cohen-Lenstra heuristics, which they're just it's a conjecture from 1984. They're called heuristics, but there are some reasonably precise conjectures made. For example, I'm just going to say the case of real quadratic fields for a random real quadratic field K. So I'll just say, when we say something like a random real quadratic field, what we're usually doing is doing something like taking fields uniformly up to discriminant x and then letting x go to infinity. There are a lot of interesting questions in arithmetic statistics about, in various situations, how one should order the objects, meaning like, why did we choose discriminant here as opposed to some other invariant? But I will sweep that under the rug in this discussion, because today I'm mostly interested in the distributions that we think arise and not necessarily the details of the ordering, even though there's lots of good questions there. So what the conjectures, one of the things that the conjectures say is that for all finite abelian groups A of odd order, the probability that the odd part of the class group is isomorphic to A. I'll just pause here a second to say that the reason that we're talking only about the odd part of the class group is that the two torsion in the class group is controlled by genus theory, so it has this very predictable behavior. And so Cohen and Lenstra, in their original conjecture, restricted to the odd part of the class group of quadratic fields, because that was the mysterious random part. So they predicted that the probability that you would get some particular group A was proportional to the inverse of the size of A and the size of the automorphism group of A. And on the top here, there's a constant. I'll put in the constant. This is a product over primes, the one that I call P. And we've got the, it's not that mysterious. It's almost a product of zeta values, except that we threw out the prime 2 because somehow the prime 2 is not involved in this. This is just about the odd part. But they guessed that the probabilities are inversely proportional to the product of the size of A and the size of the automorphism group of A. And at the time they were making the conjecture, one big motivation was to try to have an explanation, say, for class groups of size 9, where they might be the cyclic group of order 9, or they might be the exponent 3 group of order 9, Z mod 3 cross Z mod 3. Why was the cyclic group appearing more often, even though you might think, well, to get class number 9 is somewhat hard, but it might occur sort of equally often for different possible groups, but it doesn't empirically. And this automorphism factor, it explains conjecturally that difference. And it also really emphasizes here the extent to which there are really truly distributions of groups that are meaningfully arising here. If you had tried to study these distributions as distributions of class numbers, just the size of the group, these formulas, I mean, of course, you could sum this formula over all the groups of a given order, but it just becomes a kind of meaningless mush if you don't see that what's happening is that you are summing one over the size of automorphism groups, and this really emphasizes the fact that it's really a distribution of groups. And even if you just cared about the p torsion and you think, well, that's a FP vector space, it has a dimension. These factors arising really show the relevance of the groups. So okay, so what I want to say here is that this, I mean, this wasn't known at the time in 1984, but this distribution is an example, and maybe our first example of a universal distribution of groups. So this is a universal distribution, and I'll give maybe one theorem. So in this form, this is in a paper of Hoi Gwyn and mine, which says that if you make a random abelian group in a certain way, so let's let M be a random n by n plus 1 matrix with IID entries from a distribution C on the integers, so it's a random integral matrix, and I'm going to say almost nothing about the actual distribution itself. So that's the universality, that I'm building a random matrix with independent entries, but I don't really care how you pick the entries. I just have to put like the mildest possible restriction on C to make sure that it's not trivial. So it needs to take, Z needs to take more than one value mod P for all primes P. So if, for example, the random variable was always 2 mod 3, then mod 3 you really are not getting a random matrix. So that's really sort of the mildest possible way integrally to say that this is a non-trivial distribution. If you do that, and then okay, well, those are some random matrices. Where are my groups? So the so for all finite abelian groups A, we're going to get our random group by taking the probability that the co-kernel of our matrix, the random group is the co-kernel of our matrix. And we're going to ask about the probability, the limiting probability, just like one does in most universality results, including results that are somewhat analogous about eigenvalues of random matrices. We take the size of the matrix infinity and we take the co-kernel. So that is just the most natural way of building a random group from generators and random relations. This is just Z to the n mod the column space of the matrix. So each we start with Z to the n, and each column makes a relation. So you can also write this like this, Z to the n mod the image of the matrix, considered as a map on integral vectors. And this is that precise. I won't write out the constant again, but it's the same as above. You can see it right there. Same probability distribution here. So yeah, so this says that, if you make one very natural way of making a random abelian group is from generators with random relations, which is kind of what you're seeing here, which you can just call the co-kernel of that matrix of relations. And no matter how you take the relations, of course, here there's some independence, but whatever kind of distribution they came from, you get the precise same output distribution, this universal distribution on finite abelian groups. And I should say that the result is actually much stronger than this. You can take the distributions changing as n goes to infinity. You can take them, they don't have to be identical. You can take them different at different places, but then you have to put on, some conditions to make sure that they aren't too quickly as n goes to infinity turning into a constant distribution. And one observation to make here about how these two things are connected, this conjecture on the class groups and then this random matrix thing, is that there is a pretty reasonably natural way in which the class group is a co-kernel. So if S is a set of primes of a number field K large enough to generate the class group, then the class group is the co-kernel of the matrix describing the map from the S units to the S ideals. And so this is just sort of a z to the size of S plus 1 by Dirichlet unit theorem. And these are just the ideals supported on the primes of S, which, by the unique factorization of ideals is just z to the S. So this is the, so, and these are units, up to S. So they can have valuations at S, but otherwise. But this is just a normal sort of way of saying, okay, we construct a class group by taking ideals, mod principal ideals, or things coming from elements. It's just saying we can do it on a finite set of primes as long as it's a set large enough to generate the class group. And then you could also take S to be larger and larger as long as it generated the class group. And so, in fact, you can really think of the class group naturally as the co-kernel of a large or even growing larger and larger matrix. Now, we don't know that this matrix is anything like the form in the theorem. In fact, when you try to write them down, it really isn't quite like that for various reasons. But this is just the tip of the iceberg of the universality class. So the universality class is much bigger than just this theorem suggests. So I'll just mention briefly a bunch of different kinds of results. So, and these are, in this approximately in these references, or maybe they cover a slightly different case, but morally it's similar. So, for example, Friedman-Washington, instead of taking an IID random matrix with independent entries, if you do something like this, like you make your n by n matrix G minus the identity, where G comes from GLN, say over the profinite completion of the integers so that there's a Haar measure, you get the same co-kernel distribution. I didn't really say what you do on this last column here, since it's an n by n plus 1 matrix, but it doesn't matter much. You can do a lot of different things. And the point is, if you're taking G minus the identity where G is from GLNZ, this is not a sort of independent entry situation, and yet you're still in the same universality class. Work of Octor from 06 and Garten from 2015 allows one to do similar things, but now maybe where you take G to be from another matrix group, like generalized symplectic matrices for certain multipliers. So those don't preserve a symplectic form, but just scale it by a given multiplier. That's the cue there. And then again, you're in the same universality class. Mazaros in 18 did a case where the M is something like uniform 0, 1 matrices among those with fixed row or column sum. So if you think about these things graph theoretically, the independent entries case applies to something like Erdős-Rényi random graphs, but this is like uniform regular graphs, which is quite a different model. There's a lot of dependence in the entries, of course, because you're trying to get to some fixed row or column sum. Again, you see here the same universal distribution. And then my current grad student, Elia Gorokovsky, is a paper from 24 where he is looking at matrices where there are block matrices where instead of independent entries, you could have independent blocks with size restrictions on the blocks, again, in the same universality class. And Elia also has forthcoming work with another student of mine, August Liu, where they do more sort of universality, finding further matrices that are in the same universality class where they actually have application to distribution of class groups of function fields. So that work is forthcoming. So far, this is just in the random matrix and the distribution of groups world, but we are already to the point where we are seeing that there are universality results that are forthcoming that can be applied to actually these questions of arithmetic statistics in some cases to understand distributions of groups arising in number theory. Okay, so of course, not everything is in the same universality class. For example, all of these I was talking about n by n plus 1 matrices. That's just because that happens to give the distribution of class groups of real quadratic fields, which is a nice place to start. But if we had talked about this whole story with n by n matrices, we get a slightly different distribution that just has a factor of the automorphism group of A in the denominator, and this is the conjectural distribution for imaginary quadratic class groups. Imaginary quadratic number field class groups. And there are some technicalities there that aren't present in the real case, which is why I mentioned the real case. And you might not even consider this a different universality class, but rather just a parameter change. So there are distributions where the probability of A is 1 over the size of A to the U times the size of the automorphism group of A, and these each arise. And so we get, just like the normal distribution, has some parameters. I would actually sort of think of all of these in one family of universal distributions with a parameter. Okay, but then there are really generally, of course, different universality classes. I'll say a bit more on this later, but if you took symmetric matrices here, as probably doesn't surprise anyone who knows about the eigenvalue distributions of random matrices, if you take symmetric matrices, you get genuinely another universality class where you get a different distribution of groups. I'll talk a bit more about that later. Um, so now, actually, already in the cases that involve symmetric matrices, but more generally, you quickly um, in this work find that you need to study um, more structures than just groups. And especially than just finite abelian groups. So as a very concrete example, I talked so far about distributions of class groups of number fields that were quadratic, but we could have higher degree number fields. And so if G is a finite group and you take K over Q to be Galois with the Galois group isomorphic to G, then the class group of K is not just a finite abelian group, it is a finite G module or a module for the group ring, C of G. So it's not just a finite abelian group, it's naturally a module. And of course, that's true for degree 2 extensions as well. But so when G is Z mod 2, generated by some sigma, sigma acts as -1. So every finite abelian group has a natural action of Z mod 2Z, which is just multiplication by -1. And it happens that in the case of quadratic extensions of Q, that's precisely how G acts on the class group. So there's no further information by treating the class group as a Z mod 2 module. However, for every other Galois group besides Z mod 2, there is additional information there. So while for quadratic fields, this doesn't provide any additional structure, for every other higher degree Galois fields, this does provide structure. Indeed, even for non-Galois extensions, there can sometimes be additional structure on the class group where it can be a module for the Hecke algebra of a finite group. You can see about that in some work of mine with my former student Wei Tong Wang. So class groups of higher degree number fields are naturally modules for some given ring. And so one wants to then, of course, understand their distribution with that structure. And the Cohen, Lenstra, Martinet heuristics are conjectures for distributions of these class groups in sort of for general degree or general Galois group. And while I won't state, precisely the conjectures, they look very similar. And the main point in the formula is they do involve the automorphisms, but as a factor of the automorphisms in the denominator, but in particular, the automorphisms as a module for the group ring, or the automorphisms that respect the group action, sort of further emphasizing here that we, again, just like I said in the case of imaginary quadratic fields, if you just tried to study class number, you would really be missing the phenomena here. Similar, if you just tried to study class groups, once G is bigger than Z mod 2Z, you're sort of missing the phenomena that they're not just groups, they're G modules. And we expect, or I would conjecture, I will just conjecture here that these are all universal distributions So some result that is in this direction is from Eric Yan in 23. So if R is a Dedekind domain, so with finite quotients, non-zero ideals I, so like the ring of integers in a number field or function fields, so e.g. R equals okay, and M is a random. We'll just do that case that we did before for consistency, but there's really nothing special about n by n plus 1 matrix with IID entries from a distribution on R. So again, this is going to be analogous to the theorem that we saw above, and we have to make some assumption to make sure that it's not a degenerate distribution here. And it's a little more complicated over general R. So here we have to say, and you can see that you have counterexamples, otherwise not on a proper affine subset of R mod P for any prime ideal P. So when our ring was just the integers, the prime, the Z mod P was just FP, and the only affine subsets of that are elements themselves. So this just said it couldn't be restricted to an element. But once R mod P might be a finite field that isn't just a prime field, then it has FP subspaces, and you can't lie on those FP. You can't lie on a single FP subspace or one of its translates without running into sort of degenerate issues. But okay, that's just, otherwise as long as like you're essentially saying that there is really some randomness or spread at all in the in this distribution on R, but you have absolutely no control over the details of the distribution, you again get a limiting universality theorem where we have, sorry, I put those in a different order, but where you have a constant distribution that is inversely proportional to the size of A times the size of the automorphism group of A as an R module. And this essentially, so there's this conjecture, this at least in spirit covers the case of G abelian here, because these group rings, of course, they're not Dedekind domains. They're generally not domains, but at least at the primes that aren't thrown out for reasons like we threw out 2 for the class groups of quadratic fields. So at the primes that aren't thrown out for genus theory reasons, these are, in the case that G is abelian, essentially products of Dedekind domains. And so this kind of universality result could be applied to see that the Cohen-Lenstra-Martinet heuristics conjectural distributions are universal when G is abelian. But I expect that it is true more generally. It's true for every G, and that would be a good thing for us to understand. So this was an example of one further kind of structure that you might care about besides the distribution of groups, distributions of modules, maybe for group rings, it could be for other things, and we see that one has universality in that case as well. Another thing that sometimes arises, also some groups of interest have pairings For example, I mentioned the Selmer groups of elliptic curves before, and those Selmer groups have Castle's tape pairing. We often think of, Shaw has the Castle's tape pairing, but the Selmer group maps the Shaw, so it also has the Castle's tape pairing. And so one naturally wants to study distributions of groups along with pairings. So those also arise naturally. I mentioned the random symmetric matrices. So in work of mine and then recent work of Elliott Hodges, one can see that if we take n by n symmetric random matrix with IID entries from one of these non-trivial distributions on the integers as above, then the limiting, we can ask about the limiting distribution. So it turns out that the co-kernel of a symmetric matrix naturally has a symmetric pairing. So it comes with such a thing canonically by being the co-kernel of a symmetric matrix. And you could ask, well, how often are those isomorphic to some particular group with its pairing? And then that is a constant over, oh, I changed my group here. Let me just make it A, because these are indeed abelian groups. A, and then the size of the automorphism group of A, with the pairing. So that's automorphisms A that respect the pairing, and then Elliott Hodges has forthcoming work on alternating matrices that would show that these the distributions that are conjecturally arising as Selmer groups from conjectures of Delaunay and Poon and Rains, and also Bargava, Kane, Lenstra, Poon and Rains, Bargava, Kane, Lenstra, Poon and Rains, are universal in the sense that they can be built via these processes where you have no control over the input distributions. You combine them a lot in a certain way, and you see these same distributions. So what we've just seen here are a couple of examples where what is arising and where the distributions we're trying to understand in number theory are not just abelian groups, but they come with some structure. Maybe it's an R module structure, maybe it's a pairing, maybe sometimes, of course, we have both an R module structure and a pairing, and that these algebraic objects, the modules with the pairings and so forth, those also are universal distributions, and their universality results in universality phenomena in different universality classes for those kinds of algebraic objects. And now I want to say, okay, but all of those were sort of based on abelian groups, and especially finite abelian groups. So those are very concrete, and we can think about them in a certain sort of way because we really know what all the finite abelian groups are, and we can list them. But also we have arising distributions of non-abelian groups that are of interest. So I had mentioned before, fundamental groups of curves over finite fields. So those are analogous to taking the Galois group of the maximal unramified extension of a number field. And so that's a profinite, and as is this, because this is a tau fundamental group. So these are both profinite non-abelian groups. And while I will say that so far in this theory, while one doesn't have to stick to abelian groups and you can add extra structure, the fact that the groups are finite or profinite, that the structures are finite or profinite, is really important to the theory as it's been developed so far. So that might be a new frontier if one needs to push beyond finite and profinite groups. As some example of that, another group that I've studied with Will Sawin is the distribution of the fundamental groups of random three manifolds. But here, what we really study are not the fundamental groups of random three manifolds, but the profinite completions. So we really just study, if you don't think about profinite completions a lot, this is like understanding the set of all finite quotients. It's basically exactly the data of all the finite quotients of a group. Okay, so as a rise mathematics, so the distributions, these are examples of, if you take a random curve over a finite field or a random number field or a random three manifold, in all of these cases, you would get a random profinite, generally non-abelian group. And so these distributions are arising, and their universality is very interesting, but we know much less. So before, we were using as our kind of first example of a universality result, taking a random matrix co-kernels, though, as you saw in that first example, there were lots of different ways that you might take the random matrix. And if you think about what that sort of meant in terms of taking generators and random relations, you could try to generalize that to trying to understand random groups from generators and relations. So Yuan Liu and I did that in a paper from 2020. So if we let FG be the free profinite group on G generators, and one great thing about the free profinite group is that there's a natural way to take relations. So these relations are going to be these Ri, and we can take them from Haar measure because we took the free profinite group. So this is not a universality result that I'm stating here, just to be clear, because I took I am building a random group, but I'm building it not in some arbitrary way where I'm insensitive to the input, but I am building it by taking very precisely the inputs from the nicest, most symmetric distribution. And in that case, we found that the random group that you build by taking the quotient of the free group by your random relations converges as G goes to infinity, so that's like letting the size of the matrix go to infinity, to an explicit random group that we described with formulas. But a big question and conjecture is this a universal distribution? In our paper, we mention only the first hint of universality, where you can do something like, instead of taking Haar random relations from a free profinite group, you could start with just a free group and you take relations in some way that takes relations up to some length and let the length go to infinity, but then you could sort of choose your length in some words. You could choose the elements that your relations are words in, somewhat arbitrarily, and you get the same result. But compared to the kind of flexibility we saw in the abelian case, it's just really the first epsilon of universality that we see in our paper. So I would say substantially this is, really wide open, but very interesting. And I certainly expect that not only is it universal, but that as we see some kinds of universality that will also have some number theoretic applications. So that's a sort of first example of a kind of potential non-abelian group that would be universal. So a more complicated model that is not just this, but has to take into account various structures like a G action and so forth, and certain number theoretic phenomena that we know to be the case, arises in my work with Yuan Liu and David Zurich Brown. And we see that it agrees with the distribution of fundamental groups of certain random curves over finite fields in a Q goes to infinity limit. So this is still, I just want to say, not a universality result. This is a result that a certain distribution, which isn't exactly this, but it's kind of in this line of distributions, arises in a particular number theoretic or arithmetic geometry example. So this is just to say that these kinds of distributions do really arise in number theory, and I'm very interested to better understand, especially in the non-abelian setting, their universality. And so part of the reason that this needs to be more complicated model is because we look at curves that are G covers of the line, and so we need not just non-abelian groups, but we need a G action. So you can't call that a module anymore because the underlying group is not abelian, but you have like an object, it's a non-abelian group with a G action. You have to work sort of in that category. As another example of these kinds of distributions, arising from objects that are naturally occurring and of interest, I mentioned before this three-manifold case. So in work with Will Sawin, we study the distribution of the profinite completions of random compact oriented three manifolds, which, if you're interested, we get by taking a random Haggard splitting, so gluing two genus G handle bodies by a random element of the mapping class group. That's just one way to get them. But of course, by universality, I would expect that many other ways of getting random three manifolds would give this same distribution on fundamental groups. But we found, one sort of technical point in our work was that we found that the right object to study is not just the group itself that we care about, but the pair of the group and a class in the third homology of the group that arises from, so that's a pi 1, from the fundamental class of the three manifold. So of course, a three manifold has a fundamental class in its third homology group that turns out to give a fundamental class in the third group homology group of its fundamental group. And the pair of the group with the fundamental class was much more amenable to study and to formulas and analysis. And so the objects that one needs to study can have more and more algebraic structure. Like here, this comes with a fundamental class. When we do something with G curves over the projective line, there's a G action. Now we're studying something where there's a G action and a fundamental class. There becomes more and more structure. And by far, the empirical observation is that it is always better to study all of the structure that is provided naturally when trying to understand these distributions. But that gets us into trying to now understand probability distributions on more and more complicated algebraic objects with actions and gadgets and classes and homology and so forth. And so I just want to sort of advertise sort of a key new tool in especially this recent work of mine with Will Sowen is in another paper of ours, the development of a moment method. So this is recognizing, this is in the sense of the moment method in probability of recognizing a distribution from its moments, or if you want to try to see a bunch of things have the same distribution because you're proving a universality result, maybe you want to say, oh look, they all have the same moments, then we can deduce they have the same distribution. So we've developed a moment method for distributions of random objects in, I'll just say, rather general categories. So, for example, it includes the category of pro-finite groups with the pairs, the category of pairs, pro-finite group with an element of its third group homology as just one of many, many things, and you can add the G action. And so this is quite more general. It's not like thinking, oh, abelian category or something. These are quite more general, not arbitrary, but many things that arise can fit into our framework, so that one does not have to sort of go around for every specific instance and redevelop at least the moment method theory for understanding random objects. Now that you care about, well, I have a non-abelian group and I have a pairing on it and an action and a pointed, maybe I have an element and so forth. And already this, we're applying this approach in our work. It's applied in our three manifold paper and in some of our forthcoming work, which is actually already posted on my webpage about curves over finite fields. But there have been many other applications. Some of the above work I mentioned, including Elliot Hodges, and also great recent work of Huygens and Roger Van Pesky, that is applying this moment method to different categories like flags of abelian groups, or different, just different algebraic structures that are arising to help see universality. So as a summary, I just want to end by saying that universality in the case of non-abelian groups is still largely quite open, and I think quite interesting and possible to have some great applications. But as some indication that it's not hopeless, there is a quite general method, at least for recognizing distributions from their moments, that could possibly be applied to help us understand this kind of universality. Right. Thank you.
Very much. Thank you, Melanie, for a beautiful talk. Any question for Melanie? Yes, Peter. Maybe I'll go because, share the mic.
Hi, Melanie. Do you have an example? Often when you make random constructions, I mean, here you're explaining statistics, but in many cases, one constructs something that you don't know exists before by showing the random thing has the property. Do you have any example where any of your random constructions, especially here with like random, Gromov made property T groups with putting more relations. So do you have any such example?
Yes. So Will and I in our three manifold paper, we really emphasize such examples, and because of what we're studying are really the profinite completions. What we can understand well is whether there are three manifolds that have certain finite quotients or don't have other finite quotients. So, I mean, just as an example, which I think is not known how to do without our probabilistic method, as a result of our finding the distribution, we show that there exists, a three-manifold compact-oriented three-manifold with its fundamental group having a finite quotient, i.e. it has a covering space with group, like you can make a group of order 120 like this. This is called a generalized quaternion group, which came up a lot in the study of which finite groups can appear as three manifold groups. So this is a finite group. You use the quaternion group with two different order 2 maps to act on Z mod 3 and Z mod 5. It is not the fundamental group of a three manifold, but there exists a three manifold that has this finite group is a quotient, but no quotient, not a quotient to H, and this is true for separately, for any H that's not a quotient of the above. So for any, you just pick a large group or a simple, group or something that is not literally a quotient of this specific generalized quaternion group. This is just like the first example, but we have quite a general theory in our paper, and we can show that there's no three manifold that we show that there is a three manifold that has this kind of covering space, or its fundamental group has a quotient to this group, but for your favorite group H, it does not have H as a quotient of its fundamental group. And so that's a kind of existence in three manifolds that we are able to show via a probabilistic method where there's no other kind of construction known. And we emphasize this a lot in our three manifold paper. It's a great question. We have not emphasized this as much in the results for fundamental groups of curves over function fields, because there we just really were emphasizing getting the distribution. But it's a great point, because certainly there, in getting the distribution, there are many existence results that we would not, necessarily have had any ability to prove previously. So I'm glad. That's a great question. We should emphasize that more in the function field work, but we did talk about a lot with three manifolds.
Okay, great. Maybe a quick question, Andrew.
Thanks. Hi, Melanie. I'm not sure it's a fair question, but it goes back to the start of your talk, and it's about uniformity. So you suggested you had these matrices to model class groups, I guess when, like real quadratic fields as opposed to imaginary quadratic fields. And yeah, so I'm interested in how perhaps how fast convergence is, or in particular, whether n, the size of the matrix, might correspond to something to do with the size of a discriminant, like in Keating-Snaith.
Yes, I think that is a great question and has not really actually been spelled out in the class group case. So in the case of using alternating matrices to model Shaw or Selmer groups of elliptic curves, we thought very carefully about how the size of the matrix would relate to the height of the elliptic curve in my work with Bjorn Poonen and John Voigt and Jennifer Park, where we discuss whether, what you should think about the distribution of ranks of elliptic curves and boundedness of ranks of elliptic curves. So we thought about, quite carefully how you should calibrate to tie the size of the matrix to the height of the elliptic curve. So that's an example of that kind of thing that's in this spirit with the random matrices. But in fact, I think that that John Boyd had a student who did some thinking about this in the case of class groups, but I haven't really seen yet a good theory of that being worked out. So anyway, but that's a great question, a great suggestion, and definitely would be interesting to do that for the class group situation and see what it might tell you.
Thank you.
All right, I think we're out of time. So let's thank Melanie again. Thank you so much.